video, we are going to look at exothermic and endothermic reactions. We're going to talk a little bit about what exo and endothermic reactions are and what it means by what's the definition of those two words. We're going to then look at reaction profiles, being able to draw reaction profiles, that's sometimes expected of you, but also being able to label the key parts. So we're going to look at that. And there's a required practical here. So we're going to talk through the required practical and really talk about the types of questions you get asked in regards to that. And then we're going to look at cells and batteries and fuel cells as well. And so this video in itself should probably last about half an hour. We'll see how we go with it. But we'll get started. We'll jump straight in terms of what we mean when we're talking about exothermic and endothermic. So we'll start off with just thinking a little bit about the words. So I want to start with the word exothermic. Okay, so exo means to give out. So think of the word exit, and thermic means heat, energy. So it gives out heat energy to the surroundings. So it's important we know that. So let's actually write that down as a definition. So an exothermic reaction gives out heat energy to the surroundings. So I would expect the surroundings, therefore, to get hotter, and the temperature would increase. Okay, so you want to maybe think of it, if I draw a little diagram, if I've got an exothermic reaction, then the energy is moving out into the surroundings and therefore making the surroundings warmer. Examples of exothermic reactions. Well, most reactions actually are exothermic, but you've got neutralization. So neutralization reactions are examples of exothermic. You've got combustion, which we know is the fancy word for burning. You've got those hand warmers. I've seen questions where they're asking about hand warmers. Don't even ask. But obviously the hand warmers are chemical reactions that you snap, and it then creates a chemical reaction that gives out energy to the surroundings, so therefore is an exothermic reaction. On the other hand, endothermic. Okay, so thermic we know is heat energy, and endo means to take in. So again, we're going to define that. An endothermic reaction is one that is going to take in a heat energy or energy from the surroundings. So an endothermic reaction takes in energy from the surroundings. So as a result, the temperature would decrease. So the solution would the surroundings would get colder. So again, we're taking that energy in from the surroundings, and as a result, the surroundings will get colder. So examples, ice packs. You also look at it, might hear of something called anhydrous copper sulfate. But there's not very many reactions that are in fact endothermic. So how have I seen this come up? I've seen it come up in a couple of ways. You might have to identify whether something is an exothermic or an endothermic reaction, and usually that's by the temperature change. If it's gone up, it's exothermic. If it's gone down, then it's endothermic. You might have to define the word, so know exactly what the word means. So that's what we're talking about when we're talking about energy transfers. They are the two things we need to know, exo and endothermic. And what that then leads on to is something called reaction profiles, and you often see these reaction profiles in exams. For foundation tier, they will usually give you a diagram that is labelled and you have to identify what parts there are. And for higher tier, you might be expected to draw them when you only know the reactants and products energy. So we're going to talk a little bit about reaction profiles, how we can then use those to work out whether something is an exothermic or an endothermic reaction. What are the key labels we need to be able to identify? And I'm going to do that on the top one, and then I want you to see if you can do that on the bottom one before we then go through it. So the first thing I want to draw your attention to are the labels, and I have seen exam questions where you have to remember these labels. So know that this is the potential energy and this is the reaction pathway. So when we're talking about reaction pathways, we're talking about reactants and products. Okay, so here is what I'd call, well, we're going to label it, we call it A and B. So A would be my reactant energy. So the energy that the reactants have. So if you remember from the fundamentals video, A plus B gives me C plus D. This here is my reactant. So they're going to react together. And to do that, they have a certain amount of energy. And they're going to make my products. And again, I may have a different energy level. So B is what we call our products energy. And like I said, you may be expected to label these. So it is important you know what they all are. So we've got potential energy on the y-axis, the reaction pathway. I have my reactants turning into my products. Here's my reactants energy. Here's my products energy. Now in between, I have something called the activation energy. Now what I do want to mention to you is activation energy begins where the reactant line is. Okay, and so that's the bit that the examiner's trying to trick you. So you want to go from the reactants line to the middle, and then it's about drawing a line up like that. And I'm going to label that C. And C here is my activation energy. And that is the energy that is needed for the reaction to take place. And it comes up in paper 2. So energy needed for reaction to take place. It comes up when we come to talk about catalysts and how actually catalysts lower activation energy. So just be aware of that. And then the final thing I want to show you is this line here, which is the difference between the reactants energy and the products energy. And I'm going to label that D. And D is my overall energy change. Now I can see from this reaction that my overall energy change is in fact negative. Can you see how the reactants energy, it's gone down, so energy must have gone out to the surroundings. So I can tell from this, because my products have a lower energy than my reactants, that this is showing me an exothermic reaction. Okay, and I know that because these guys always have a negative overall energy change. So always have a negative overall energy change. Okay, and that's indeed what that would be there in this example. So what I'm going to get you to do is just pause the video, take on board what we've discussed here, and see if you can then label this specific diagram. And again, try to explain why it might be showing an endothermic reaction. So pause the video and give that a go. Okay, so hopefully you'll be able to do that. Let's just check. So we've got A, which we know from above is our reactants energy. We have B, which is our products energy level. The labels are the same, and again, like I said, you do need to know these labels because you might be asked to label a diagram, and I have seen them ask you that. To draw the activation energy, you have to start at the reactance energy level and then draw a line up to the peak. I don't quite draw a straight line there, but up to the peak like that. This is C, which is the activation energy. Okay, and then the difference between the reactants and the products would be D, and that would be my overall energy change. And in this case, I can see that my overall energy change would be in fact positive. And that tells me I've then got an endothermic reaction because energy has been taken in from the surroundings. So the overall change in energy would have a positive value. And so that is your reaction profiles. Like I said, you need to know what each of the 4 parts are on the diagram, but you also need to be able to label those diagrams too. Okay. The next thing I want to talk to you about is the required practical, which is one of the assessed practicals that could in fact come up. And if you've ever attended one of the Strive sessions, you know that we've done this required practical as a practice one. And there's a couple of things that are really within the question that can help you to answer this type of question, but we will look at the required practical here, which, as the question says here, we are investigating variables that can affect the temperature changes in a reaction. And the key thing is about knowing we are investigating temperature changes. And when you see that come up in any exam type questions, then the first thing I want to pop into your head is this idea of the polystyrene cup. Okay, so polystyrene cup experiment is the one we're talking about here when we're talking about investigating temperature changes. And so here is essentially what we would do, the types of questions that would come up, and really the method you'd expect to be kind of writing about. So what we are essentially looking at here is to do with energy. And energy is released from the chemical reaction, and we measure the temperature change of the solution at the start and at the end, and we use a polystyrene cup. Now, equipment-wise, so let's just kind of go through this. So as you can see from the diagram, we have our polystyrene cup, and again, I've seen questions where they ask you what's wrong with the experiment, and they might use a glass beaker, for example. So polystyrene cups we know are insulators. So therefore, any energy change taking place in the reaction will stay in the reaction rather than being lost to the surroundings. So an important piece of equipment. You've then got the lid. And again, that's an important piece of equipment because the lid stops evaporation. So heat being lost from the experiment. So a lid again is an important factor, and it's important to know that without these, this is what we'd call random error. So if you remember the 3 types of error, so it's random error, systematic error, and zero error. We should never be saying human error for any answer. But here we can see we've got a random error because the person might have left the lid off. So therefore heat can escape, so the energy change would be greater. We've then got, we might have, but we don't always have in the experiments I've seen in exam questions, but things like cotton wool are an insulator. They're just extra insulation to stop the heat escaping to the surroundings. Okay, we've got our thermometer to measure the temperature change, and as we're trying to show factors that can affect temperature change, we'd have our factor, okay, would be on the left-hand side because that's my independent variable. And then I'd have my temperature at the start, temperature at the end, and then the overall change. And then the greater the change, the greater the amount of energy being lost to the surroundings, for example. Okay. So what types of experiments does this usually come up with? So it usually comes up with things like neutralization reactions. I've seen it asked linked to the reactivity series, where you want to demonstrate that one metal is more reactive than the other. So we know that if there's a greater difference between metals in the reactivity series, they'll give out more energy. So it just depends on what they're asking. So I'm going to look at this from the example of a neutralization reaction. And we are going to look at this in terms of we're investigating the effect of different variables have on the amount of energy. So we might, for example, want to see how concentration of acid affects the amount of energy given out in the reaction. So I would have my 5 different concentrations. I would have my acid added to my polystyrene cup. And this is where you need to remember SID, SAM. Okay, so my control is what we keep the same. My independent is what, I can't spell, independent is what we alter, so what we're changing. And my dependent is what we measure. Okay, so my acids, because I'm changing the concentrations of acid, that would be my independent variable. The type of acid, the volume of acids, that would be my control variables. Okay, so type, volume of acid would be your control variables. And then we might add magnesium metal to the acids. So beforehand, we'd take our starting temperature. We'd then add the magnesium metal to the acids, replace the lids, start my stop clock. So again, I'd need to have it for a fixed time. And then I'd measure my temperature at the end, and I would look to see the overall temperature change. So what are you generally expected to do? You need to be able to write me a method. So again, we'd be saying I do this as bullet points, and I think it's important that you're brave enough to do that, because it just helps you lay it out. I would always do it as bullet points and then go back and number it afterwards, just so you've got the order in the correct order. So if I wanted to investigate the different concentrations of acid and how that affected the amount of energy given out in the reaction, I would have, first of all, collect equipment. Sometimes they give you the equipment. Secondly, I would have 5 different concentrations of acid, and I might want to tell the examiner what I mean by that. So 20%, 40%, 60%, 80%, 100%, or I could do 0.5 molar, 1 molar, 1.5, 2 molar, 2.5. Okay, so I've got my 5 different concentrations of acid. I'm then going to measure, 30 centimeters cubed of acid at first concentration and pour into my polystyrene cup. Okay, I would then take the temperature and write that on my my table, and then the next step would be to leave for, you could make a time up, or you could say until it reaches the highest temperature. So to leave for, 5 minutes, retake temperature, and then work out the temperature change. And then usually the question is asking about a valid method. And when it's asking about valid, you then repeat, okay, to make sure that you're getting valid sets of results. But you'd also repeat with your next concentration and do the experiment again. You may want to also include about the idea of a lid to stop heat escape, polystyrene cup to stop heat escape, what your control variables are in the experiment as well. So hopefully that just jogs your memory about this idea of temperature change, energy changes. Obviously, if you've got a higher concentration, you would expect a higher temperature change. So you're linking patterns to the conclusions in the data. If we were looking at the reactivity of metals, the greater the difference between the metals in the reactivity series, the greater the energy change. What I'd suggest to do is actually have a little look online and watch the practical so you can get an idea for how the practical actually works. And hopefully that gives you an idea of the required practical for this particular subject. Okay, the final thing I want to look at with you is bond energy calculations. What I will say is this is where foundation tier and higher tier splits. So this is only expected in higher tier. So if you are a foundation tier, I would fast forward through this section until you get to the next part, which is looking at cells and batteries, because you don't need to be able to do this. But if you're higher tier, you're going to stay with me, and we're going to go through what we call bond energy calculations. And I'm going to give you two examples of these and how to do them. And hopefully that will help to explain to you how you would actually carry out bond energy calculations. I actually quite like these. I think these are quite straightforward. What I'd probably suggest you do is pause the video, have a little look, see what you think you do, give it a go, and then we'll go through it together. Okay, so let's see if we're clear on how we do this. So this is a typical bond energy question. It's quite a nice easy one because it's low in marks. Sometimes these are 5 markers, and I'm going to do a 5-mark question with you. But essentially what we're trying to do is we're trying to work out the overall energy change in the reaction. So the question says here to calculate the overall energy change for the reaction that is shown in the diagram above. And it's given you the reactants and the products with all the bondings, the molars, moles, and etc. of each molecule as well. And then you're provided with a table that tells you the value of one bond. So if I've got an NH bond, one NH bond has a value of 391. Okay, so I always lay these questions out in the same way, and I think it's important to do that for the examiner. It just explained your reasoning. So what I always do is I always split the lines into each half. So we're looking at the reactants on this side, and we're looking at the products on this side. So I'm going to use, the real tricky bit here is working out the number of each bond that you have and then being able to put those numbers into the table. So we'll start off first of all with this molecule here. So I can see it's got a 4 in front. I'm just going to cover that over. And I can see that there are 3 NH bonds. Okay, so 1, 2, 3. And in total, we're doing 4 times this molecule. So that means we've got 4 times 3. So we know that therefore there are 12 NH bonds in this molecule alone. So I know that 391 is the value for 1. So I would do 12 times 391. And that's going to give you the energy for that, for breaking the bonds down there. So 12 times 391 gives me an energy value of 4692. I then look at my oxygen, and I can see that my oxygen is quite a straightforward one. I've got 3 oxygen bonds. So times that by 12, I'm timesing this one by 3. So 3 times 498. 498 times by 3 is 1494. So in total, on my reactant side, I have an energy value of those two added together. So 4692, 6186. So that's my reactant's energy value. I'm now going to look at my product's energy. So again, I'm on this side of the arrow. So on my dotted line down where the arrow is, nitrogen's nice and easy. I've got 2 nitrogen bonds there. So I'm timesing that by 2. So 2 times 945 equals that. 945 times by 2, 1890. And again, when you've got molecules like this, you cover over that number first and work out how many bonds you've got. So I can see I've got 2 OH bonds, but in total I'm multiplying that by 6. So we know 6 times by 2 equals 12. So in total I am timesing that by 12. I've got 12 OH bonds there. So I would do 12 times 464. 464 times by 12, and that gives me 5568, and I then add those two numbers together to get the overall product energies value. So total energy is 7458. And then this is the bit that people usually slip up on. It's knowing what you have to do now. And the key to this is knowing that you have to essentially find out the overall energy change. And the overall energy change is the energy required to break the bonds. Okay, so that's essentially the energy on the reactant side. Take away the energy released from forming the bonds, which is that of the products. So essentially I'm doing 6186 take away 7458. So I'm just plugging the numbers into my calculator. Take away 7458. And that gives me an overall energy change of 1272. Now, if you notice there, I've got a negative overall energy change. And this is where this can actually link back to when we were talking about reaction profiles. Because we said earlier that if you've got an overall negative energy change, then that's an indication that you've got an exothermic reaction. And lo and behold, the next part of the question is, explain why the reaction between ammonia and oxygen is exothermic. And I've got to use my value from the question before. This is often a 2-mark question, okay? So the first thing I'm going to say is, well, the overall energy change is negative. And that tells me that energy, that tells me that energy has been lost to the surroundings. So what I'm hoping you can see here is that it ties in with the reaction profiles. A negative energy change is an indication that you've got an exothermic reaction. And if it was a positive energy change, then you'd know it's an endothermic reaction because energy has been taken in from the surroundings. So that's one example of bond energy calculations. I want to show you another one, okay, which is a little bit more complicated. As you can see, it's worth 5 marks, but this is the one that I've seen more often, particularly on higher tier papers. So again, the principle is the same, but the key to this is reading the question carefully, because a lot of the information that you need is in fact within the question. So let's start by bugging the question. So figure 2 shows the displayed formula equation of the reaction of hydrogen sulfide with oxygen. And the table below shows the bond energies. So I can see the bond energies for each one, but lo and behold, I do not know the value of that specific bond. And the question is going to get me to work out what the value of one of these bonds are. So it says, in the reaction, the energy released from forming new bonds is 1034 greater than the energy needed to break the bonds. So I know that the reactant's all about breaking the bonds, and I know the products is all about making the bonds. So it says in the question that energy released from making new bonds over here is 1034 times greater. That's how much more energy it has than over here. So if I know how much energy is here, then I can actually work out in total how much energy should be here. And that's then going to allow me to work out this X value. So we'll work through it. What I maybe suggest you do is, again, just pause the video, give it a go, think about how we laid it out in the last question, because I'd be expecting you to lay it out in a similar fashion here. Okay, so hopefully you've given that a go. So again, I'm going to draw my dotted line down the middle. I'm going to have my reactants on this side and my products on the other side. And I can work out the energy over on here. I can work out my reactant's energy value. So again, when you've got molecules like this, you cover it over to start with. You count how many there are. So there are 2 SH bonds there. But in total, I'm multiplying that by 2. So 2 times 2 is 4. So I've got 4 times HS bonds. So I would do 4 times 364, which equals 4 times 364, 1456. Oxygen's quite straightforward because I'm just multiplying this one bond by 3. So I'm timesing that by 3. So 3 times 498, 498 times by 3 is 1494. So the total energy of my reactants are those two numbers added together, which gives me a value of 2950. Okay, this is where I then go back to the question, because it says, in the reaction, the energy released from forming new bonds is 1034 greater than the energy needed to break the existing bonds. So in other words, my product's total energy has got to equal 1034 more than this value here. So to work that out, I'm going to do 2950 plus 1034. So the total energy value over on this side should equal 3984. So I've got to then work out, well, how much of that is my bonding here, and then how much of the bond value is it here. So I'm going to do that now. So that's my total energy value. So I'm going to work out the energy value of the bonds here. So again, it's one of those funny diagrams. So I cover it over. I count how many I've got. I've got 2 there, and then I multiply that by 2. So I'm timesing that by 4. So 4 times 464 equals 464. 4 times by 4. 1856. And I don't know what this value is, but I can work it out because I know this is a total value. So if I do 3,984 take away 1,856, I know this answer must be the value of all of that. Okay, so 3984 take away 1856 is a value of 2128. Okay, and then I want to know what one bond is. So I've got to know the whole thing here is a value of 2128. So again, it's one of those funny diagrams. So I cover it over. I've got 2 SO bonds and I'm timesing it by 2. So in total, I have got 4 of those bonds. So if that's the value for 4 all added together, for one bond, I would divide that number by 4. And that gives me my answer, which is 532. And that's why it's a 5-mark question. It does often come up, like I said, on the higher paper, But guys, that is exothermic, endothermic. I'm probably going to split the fuel cells and batteries into a separate video because this all kind of goes together, whereas that is a little bit separate. So hopefully you found that useful. Like I've said, if you're not sure on something we've talked about, please don't hesitate to ask within lessons. It's not a normal setup. We're literally going through the content. But like I said, hope you found that useful, and I will leave it there. Thank you.